Let's take a look at homework number 10 here. So considering the following data, which is the number of traffic accidents involving children within 2 kilometers of schools listed by days of the week. So you've got the Monday through Friday spread there. Let's consider a hypothesis which states that no pattern exists in the data, i.e. there are no peaks in the data and everything occurs uniformly. If this were true, we'd expect there to be roughly the same number of accidents each week or each day of the week. So we're going to test it 5% significance. So that's our alpha right there. So this is alpha. And if you add these up here, we have n equals 100. So that'll come in handy here. So we're looking for the expected counts. Well, if they're all supposed to be roughly the same, then we're looking for all the proportions being the same. We're dealing with qualitative data here. So each expected count EI, all of them are going to be this 100 over 5, which is 20. So all of these are 20. Now, the null and alternative, we can write something similar to, the proportions are the same versus proportions are not the same. This is where I typically go to here. P1, and this relates to Monday, equals P2, which is Tuesday, and we have 5 of them. And the alternative is that they're not all the same. If you want to write something along the lines of accidents occur in a uniform fashion, something like that, for our null, that'll be fine. Or not all the same. Let's see, no pattern exists, I guess. You can try that. That should work as well. What you want to try to avoid is talking about the observed values here. We're talking about the overall population, and in this case, their proportions. There's 5 of them, P1, 2, 3, 4, and 5, or P1, P2, P3, P4, P5. Essentially, the true proportion of accidents each day. Give it Monday through Friday. So, again, just be careful of that. I give a lot of latitude when grading this, so shouldn't be too bad. If you did something wrong, please see this or look for other options. Check the conditions. Well, we're looking for a random sample. We'll just say yes to that. And then the cell counts, the expected counts, have to be at least 5. And this is yes, since 20 is at least 5. So that works. We're good. Just saying that the conditions are met doesn't count. You have to actually state what the conditions are. The chi-squared. All right, so we're going to run the chi-squared goodness of fit test here. So we're going to enter the data. So stat and enter for edit. Let's clear out these lists here. Clear out list 1 and 2. And our list 2, we have 25 times, so I can do that. And again, that was kind of the whole point of this, filling in. You're given the observed counts. You have to solve for the expected counts. So that's kind of what you need to do. So let's write down what the observed counts were here. 23 was the first, and 18, 17, 19, and 23. All right, so now we're going to run the chi-squared goodness of fit test. So we're going to run this. And once we get a value, we'll put that in there. So stat tests, this one's near the bottom, so I'm going to go up. It's D on my calculator, maybe something a little different on yours, but it's the GOF version. The one above it is for when we're dealing with the test for independence, and that's a matrix. We don't have a matrix here. Observed is L1, expected L2, degrees of freedom. This is something you may have to edit here. It came up correct for me. DF is 4, which is 5 minus 1. There's 5 different options, Monday through Friday. So we're just going to go down to calculate. So the test statistic for this, and that is 1.6. And the p-value is equal to 0.809, it looks like, if I round. All right, so how does this p-value relate to alpha? Well, if you recall, alpha was 0.05. We can just do that right here. That is greater than 0.05, which is alpha, so we're going to fail to reject. So we don't have evidence indicating that there's a difference in the number of accidents. So we fail to reject our null. You can write the significance level in there if you want, but essentially what we're going to do is we're going to indicate that, so we didn't find that the number of accidents differed by day of the week. All right, so be careful here. So I've chosen to, or I've concluded that we fail to reject. Remember, p greater than alpha, fail to reject. P less than or equal to alpha, we reject. Make sure that your context conclusion is based upon your actual, what you did. So if you had said, if you say you'd come up with a wrong p-value here, say it was like 0.01 and you did reject, keep that with the conclusion. I will be checking to see that. I mean, I had some of those when I was grading these that did these wrong, but they stated their conclusion correctly based upon their conclusion. So I'll keep that in mind. I won't double dip on you. All right. This one here. So we're looking for absences during the week. We wanted to see if there's any issue with maybe people skipping out on Fridays or having a long weekend and skipping out on Mondays or that sort of thing. Here, our n is not 100. It looks like we have 60 here. So here our expected counts. We use 60 over 5, which is 12. So 12 goes in each of these. And this may not be provided for you on a given question. It may just say, here are your numbers, and test for the same or difference, that sort of thing. Just to see if there's any difference in the proportions. And you'll have to do this yourself. You have to come up with these expected counts yourself. So our null is the same thing, and P1 equals P2 equals P3 and so forth. And if you also want, that's 1/5. That should be 20% each. And here we go that they're not all the same. And if you want to write something along the lines of, we can take a look at what's written here about the number of absences. You can say maybe the number of absences doesn't differ by the day for the null, and the alternative is that at least one of the days differ from the others. Something along those lines would work as well. Conditions are the same conditions, so we'll assume randomness. And then each expected count is 12, and that's at least 5, so good. All right, let's do the same thing we did. So stat enter. Let's enter these values here. So 15 is our first and so forth. And now all these next ones are 12. And you can clear it if you want, or, there's the same amounts. It's not too bad. All right, same test. Stat tests go up for chi-squared GOF. GOF. Also degrees of freedom 4. You may have that you may have to change. All right. So let's enter this information. The chi-squared test statistic, that is equal to 3, and our p-value equals 0.558. This is, again, greater than 0.05. I think that's the alpha. We can go check. Yep, there's our alpha. That's our significance level, or alpha, so we fail to reject. And again, we don't have evidence to determine that the proportions differ. The proportions of absences by day differ. Proportions of absences differ by the day. All right, and again, I've listed above it the reason to fail to reject. You can state that in your conclusion, but you have to give it to me somewhere. Okay. Let's see. All right. Number 3. So here we have two different factors. So factor, you can say this is factor 1, and alcohol consumption is factor 2. Whatever, it doesn't matter. You can change that if you want. It's not going to change what's happening here. So we want to determine if acute myocardial infarction, AMI, is independent or dependent of alcohol consumption. So for this one, we're going to use the matrix. So seconds and the X inverse key will get us, second, and this is the X inverse key. All right, we need to edit the first one. Don't worry about the second one. That's going to be populated. And it looks like I've already got them all in. 146, 106, 29, and so forth. All right. Once you get all these entered into the matrix, you can clear out, so second mode will work. And then stat tests go up, and this time we're using the chi-squared test. A, as you observe, expected will be B. That's going to be populated, and that's what we're going to go look in a minute. All right, so we have to run the test. We've done so. We can actually go fill in some of this other stuff with this. Test statistic, that's E. So chi-squared is equal to 10.197, and the p-value is 0.0061. We'll talk about that in a minute. But we need to go back to the matrix. So the second X inverse, and let's go to edit. I'm going to edit the second one and just take a look at it. These are our values. So this top one is 131.61, it looks like. One below it is 764.39. I did not give sufficient space within the parentheses. I apologize for that. Most of you didn't really have a problem with that, however. So this is 102.24 up here. One next to it is 47.15. Below that, 593.76. And then 273.85. And those are the expected counts. All right, so let's see. And that's what part A wanted. Part B wants to set up the hypothesis. All right, our null. Again, we're talking about independence versus dependence. The null is always the independent. So congestive heart failure. That's somebody who goes through this AMI. And alcohol consumption or alcohol use are independent. And our alternative is these things are dependent. So little quotes indicating all of that is written on the second space, and I'll let you get away with that as well. All right, check the assumptions for the test. Randomly selected. We don't know. Not stated. So we have to assume. And then all expected counts are at least 5. Well, if we go up here, well, we actually have it right over there. So the smallest one is 47. So they range from 47 to 764. So yes. So 47 is the smallest, and 47 is greater than 5. So we're good. The calculator function we use is just chi-squared test. And we've put in these values here. So finally, we need something with context. So I can do this here. What is our alpha, if any? So no alpha given. Well, we got a couple options here. Typically, our default alpha is 0.05 if we don't have anything. However, that p-value is really low. That's lower than even the 0.01, which is kind of the smallest alpha that we've used. So no alpha given or significance level. So we're going to assume 0.05. And 0.0061 is less than or equal to 0.05. So we're going to reject. And essentially that means we have significance. We have significant evidence. To determine that alcohol use alcohol consumption, whichever, and what did I put? Congestive heart failure. Are dependent. Okay. And that summarizes this one again. You can state this in a couple other ways. That's fine. Just make sure you're using what's going on in the actual problem. Um, Again, I'm not talking about proportions here. It's just independence of two different factors, essentially. A few of you used correlation. That's something we're going to get to actually next chapter. So this one's independence versus dependence. Next chapter, correlation will work. Yeah, correlation will work. All right, there you have it.